Okay, so in the second part, I'm going to talk about a famous theorem. So now our topic is so-called labeled trees. So it's not nothing fancy, just easier for us to count. What is a labeled tree? So suppose we have a tree with vertices 1, 2, 3 until n. So now our vertices has names. Before we call v1, v2, v3, and now it's just a 1 until n. And then we ask the following question: how many trees? How many trees are there on this vertex set? But to be clear, when you are facing some counting problems, you have to know what kind of objects are different. For example, you have 1, 2, 3, and maybe you have 1, 3, 2. So maybe you have 3 vertices like this. They are different labeled trees. Although they have more or less the same shape, but we are dealing with them two different labeled trees. Okay, defining labeled tree is like I just said, is for the purpose of easier counting, and everything has a name. So then in this case, 2 is standing, it's a path. If you consider the shape of the graph, it's just 2 paths, it's a tree. But in the first one, 2 is in the middle, and the second one, 3 is in the middle. So in the first one, 1 and 3 are leaves, and the second one, 1 and 2 are leaves. So there are 2 different labeled trees. So with this understanding, we ask how many labeled trees in total on this vertex set 1, 2, 3 until n. So it's kind of a very famous theorem because it has a very neat answer. So the theorem is called Cayley's formula. It says that the number is the number of labeled trees on n vertices is n to the power of n minus 2. So it's a very, very, very neat number. Very clean. So let me give a proof. There are many proofs of this formula. I leave one proof, a particular nice proof, with some hints as an exercise to you. But here I give another famous proof, which is called the Prufer sequence. So in fact, given a labeled tree, I can find a way to generate a sequence with n minus 1 numbers. And if you are given any sequence and you are told that this is a Prufer sequence, you can actually reverse the whole process to locate this labeled tree. So in this process, this thing in proof is called a bijection. Okay, so the word of all the Prufer sequences. Prufer sequence is just the name. All the sequences, you can find a bijection into the world of all the labeled trees. So let me you can understand, try to understand this with the proof. Let T be any labeled tree, because we are counting them. Choose any one on the vertex set 1, 2 until n. Okay, so what happens is I'm interested in all the leaves. So for example, here I got leaf 1, 3, and here I got leaf 1, 2. But if I imagine I have drawn this tree with labels. All the vertices has name 1, 2, and so on. And I'll put S1, which is S1. Let S1 be the smallest label for the leaves, for all the leaves. Okay, for example, if I'm looking at this tree, the S1 is 1. Because I got 2 leaves. One is 1, the other is 3. And here, I got 2 leaves. One is 1, the other is 2. S1 equals 1 again. So that S1 is just the smallest label for the leaves, for all the leaves. Now, what I'm going to do is that I choose T1 to be the neighbor. I read this as neighbor of S1. So for example, I got a tree and somehow I got S1 here. And this guy. So this is the tree. I got many leaves, and this S1 is the smallest label among all leaves. And then I record T1. So I need to remember this number T1. I put T1, and then I decide to delete the leaf S1. So after I remembered T1, I will delete S1, and then I got another tree, and get a new tree. Okay? Still labeled, but S1 is not there. And I repeat the process. I continue the process. What do I mean I continue the process? I choose a leaf which has the smallest label, and then I find the neighbor of that leaf, and I call T2. And then I delete. For example, let me write another step. So in this remaining tree T, I let S2 be the smallest label. For the leaves. And then choose T2, the neighbor of S2. And then delete S2. Okay? So when do I stop? I stop the whole process. We stop when there are exactly 2 vertices left. Then I stop the whole process. And what I get? The sequence T1, T2, until Tn-1, because I do this for n-1 times. There are 2 vertices left. I have to delete n-1 vertices, and I get n-1 numbers called T1, T2 until Tn-1. On this guy, this sequence is called the Prufer sequence. Prufer sequence. Okay? So this sequence is called Prufer sequence. Clearly this can be done. But what is hard, we have to prove is that given the sequence, actually the whole process can be reversed. We can come back and obtain the labeled tree. And then I got a bijection. Okay, someone call this a Prufer code. Or a Prufer code. Prufer sequence or a Prufer code. Okay, so first of all, what is the number of total Prufer sequences? So actually, any position, any coordinates, you can choose from 1 of n. So there is no restriction. So the answer is n to the n minus 2. This is the number of. So after we prove this, if we can obtain this bijection, then we know that the number of label trees, total number of label trees is this number, n to the n minus 1. This is the correct count. So because every coordinate, I have n choices, and I choose n minus 1 times. So I got n to the power of n minus 2 Prufer sequence. Now, what's left is the following. We need, given it remains to show that, so this direction, let's just write this direction. It remains to show that given any Prufer sequence, let's say T1, T2, until Tn minus 1. So you choose arbitrarily a sequence like this. Each Ti is just one of the n numbers. And you fix it. And I can give you a way to recover the label tree. First of all, so the degrees of the vertices in T are exactly, so let me say. So the tree T will obtain finally, in the end, the degrees of the vertices of T. So you can think of the T there. So you have n vertices. There are some leaves. The degree of the leaf is 1. Remember, each Ti is a neighbor of some leaf. So for example, first step I choose S1 and I record the neighbor of it as T1. So what happens is that all the leaves, they never appear in the Prufer sequence. So in fact, the degrees of every vertex of T are exactly the number of times it appeared in the Prufer sequence plus 1. So for example, so this is you can think of and agree with me. So this is for example, the degree of leaves in T is 1. So you pick any leaf in T. The degree of that leaf is 1. And it never appears in Prufer sequence. So the statement is correct. So the number of times it appeared in the Prufer sequence is 0. And plus 1 equals 1. Okay? So if you agree this, then all the leaves, so let me write down this. All the leaves of T are exactly all the numbers that do not appear in the Prufer sequence. So in this sequence, I got n minus 1 numbers. Okay, so you can see that you record all the numbers and you find all the numbers that do not appear in the sequence, because it's only n minus 1 numbers and we have n vertices. So at least 2 do not appear there, and actually all the vertices, all the numbers that do not appear here are the leaves. So now we know the leaves. So what is S1? S1 is just the smallest of them. Like in our definition, okay, S1 is the smallest of them. So we know that, so S1 is a leaf, is the smallest of them. And T1 is in the Prufer sequence. So T1 is given. So we know that S1 T1 is an edge. Is an edge of the tree. So S1 is actually the leaf, which is has the smallest label. And T1 is the first guy in the first number in the Prufer sequence. Okay? So then if you recall the definition of how we obtain the Prufer sequence, we can think of as if we deleted the vertex S1 from T. It's like, okay, we delete this guy and get probably T prime. Sometimes we still call it T, but it doesn't matter for now. So if we delete S1 here, then the Prufer sequence becomes shorter. Okay, it becomes T2, T3, T4 until Tn minus 1. So let's remember, okay, I already remember this is an edge of my graph T. But if I forget about it and I look at this graph, this Prufer sequence, on the vertex set 1, 2, until n minus S1. So because S1 has been deleted. So suppose we don't have S1. We have a vertex set 1, 2, 3 until n, but minus S1. On this on this vertex set, and with respect to this Prufer sequence of length n minus so T minus 2. This is a Prufer sequence of length n minus 3. And we do the same. We repeat the above process. So what do we do? Remember, we find in all these numbers, all the numbers that do not appear here, and we choose the smallest one, and it is, so this smallest number that do not appear here is S2. And we know that S2 and T2 is an edge. And we continue doing this. So if I do after n minus 1 steps, we have found all the edges. Remember, each step after we finished it, we found an edge. So if after n minus 2 steps, we found n minus 2 edges, in fact. So there is one edge, I haven't found it, but it doesn't matter. It's left there. So one edge I didn't find is between the remaining 2 vertices. So here I got a question. Exercise. Understand where is the final edge. Okay. Okay, this is actually as you can see, there is an algorithm relating to this. So in graph theory, it's related to algorithms. So this is one of the algorithms, famous algorithms you probably you meet in the future. Okay. Okay. So I think I finished the plan for today. I'll send you my okay. Let me finish the recording.